So we're starting a new chapter, chapter 3. Chapter 3 is, you may have guessed, it's a lot of functions and a lot of graphing. So really, this section is the name of the section is the whole chapter, but this section in particular is kind of going to be introducing a lot of those concepts, like what is a function by definition, and what is a graph, and so on and so forth. So let's dive into it. So a function. As a definition, it's a mapping of inputs to outputs. So a mapping is just saying, okay, I'm going to take my number 2 and let's say I'm going to put it and say it goes to 4. And I'm going to take a number to number 7 and I'm going to say that has to go through to number -2. So a quadratic function, it did that. We had a lot of things going on. We had a lot of numbers flying around, but we took a lot of numbers, put it into our function, and we got a result. But in order for a mapping to be a function, there is a very specific quality that is needed to be met, and that's every member of the domain maps to exactly one output, or every number that I'm starting with doesn't get mapped to 2 other places. So I wouldn't map 2 to, okay, 2 can go to 4, and also 2 can go to -7. That is no longer a function. So to see that in practice, a few more definitions before we see it in practice. Domain is the set of all possible inputs for a function, so all of the numbers I could throw into a function. And the range is all of the possible outputs I could get from my function. Now we get to see this in practice. So this is one way to represent a mapping, or more specifically a function. And basically all it's saying is these are points. So my point 1 is my x is 1, my y is 3. My x is 4, my y is 5. My x is 4, my y is -6. Now the question we have to ask ourselves, is this a function? Because it is a mapping. I'm telling all of my inputs to go to something. But am I meeting that second part of my function? Well, if I look at it, I have 2 repeating inputs. I have 2 4s. And one of them goes to 5, and one of them goes to -6, which I'm not allowed to do by the definition of a function, so that is not a function. To see another example, I have my mapping here. I have -2 goes to -2, 4 goes to 5, -3 goes to 5 as well. And I might think, okay, well, I know in the last example there was the repeating 4, which was bad. And in this example, the repeating 5, which is bad. But what's kind of weird about the definition of functions is I'm actually not concerned about my outputs. So I could have everything mapped to the same number. That's okay. I just can't have one number mapped to 2 separate locations. So even though 4 goes to 5 and -3 goes to 5, this does meet the definition of a function. And then the question asks, if it is a function, what's my domain? My domain is my set of all possible inputs. So in this case, my domain is -3, -2, and 4. And those are found by just looking at those x values of those 3 points. And I guess I asked for range as well. And then my range is all of my outputs, so that's -2 and 5. Notice how the 5 is repeating. You don't repeat stuff if you are writing something in the range. You only need to write it once. Now this is kind of a strange case, so if this one kind of messes with your mind, don't be concerned about it. Really make sure that part A and part B make sense, but part C is kind of interesting. So again, you kind of leap out and you say, oh, okay, well, I know that having 2 input functions is usually pretty bad. That's what broke the definition of a function in part A, and that's certainly what's happening here. But it's doing something tricky. Yes, we have 2 separate inputs, or repeated inputs. We have -2 and -2, but they're actually being mapped to the same output. So even though it doesn't seem like it's a function, those -2 to 1 and -2 to 1 is actually just being redundant. And the truth of the matter is no matter what, you're taking your -1, you're mapping it to a single output of 1. So it is a trick question. It is a function. So my domain is -2 and 4, and my range is 1 and 3. Now, there's a lot of ways to represent functions. You can see it in that notation that I just write with points. You don't honestly see that too often in mathematics, but what you do see more often is tables, and you certainly see much more often equations. So let's look at tables as though they're functions. So this is a mapping, certainly. I have inputs. They are going to outputs. Now I have to see if it's a function. Well, I want to avoid having two inputs being mapped to the different outputs, having the same input mapped to different outputs. So in this case, I look at my inputs and I see 2, 3, 4, 7. So I have no repeated inputs. So I don't have to really be worried about an input being mapped to two separate outputs. So it's a function. That's kind of the nice case. If you see no repeats, don't overthink it. It's a function. Now here we have repeated inputs. We have 1 and we have 1. The first one is going to 3. The second one is going to 4. So I am mapping. That circle should be on the next one. So 1 is mapped to 3 and 1 is mapped to 4. So that is not a function. Again, to be clear, 3, 7 should not be circled. 1, 4 should be circled. Now, function notation. So sometimes we only have one function, and it's almost silly to kind of say, okay, I need to be careful about how I name my functions. Like, if you are just drawing one line of a graph, there are no other equations. It's just y equals, I don't know, something like 2x plus 3. But quite often we deal with a lot of functions. And that's why this function notation comes about, is we want to be able to describe different types of functions, and then we want to say, okay, I'm going to use this one, and I want to use this type of output. And so that's why this comes about. It's just a way to name things. And so this example says, let's say you have your first 3 scores on your test, 87, 72, and 91. And you want to write a symbolic rule for your average over 4 tests. So even if you didn't know function notation, you would probably say, okay, average, I add up my numbers, and since I have 4 of them, I divide by 4. So 87 plus 72 plus 91 plus whatever you want to call your variable. You don't really know what your last test is. I said it was S. You could have said it was X. That's perfectly fine. And it's all over 4. But I want to be able to name this function, and so I'm going to name it A for average. And my input, since I have an S in my function, that is going to be my input. So that's what that little guy tells you. So the outside, the big capital letter tells you the name of the function. Whatever is inside the parentheses tells you what the input of the function will be. So quite often the most common function that we see is f of x. But it doesn't always have to be x. So it could be, in this case, a of s. You could have multiple inputs, in which case you should probably put a comma between them. But that's really what's happening, is we're naming the function, and then we're saying, this is the input that I'm going to be dealing with. This is the variable that will be changing. And so I've kind of already said it a couple of times. But how you would say that is a of s. So you would say the name of the function, then you say of, and then you would say your input. So anytime you hear f of x or a of s, that's what we're talking about. We're talking about the function notation. Now, if I was asked to find the average of what you got, find out the average if you got a 94% on the last test, well, that's a very long-winded way of saying my input is 94. And so I'm really trying to find what A of 94 is. So notice how my S is gone now, and I've replaced it with what my result was. My final test was my 94%. And so really that left side is not, we're not doing any math on the left side. All we're saying is we use the function A and we plugged in 94 in for my input. But notice how the right side of the equation, the S is gone and now has been replaced by 94. And so then we just do some basic order of operations, and we see that A of 94 is equal to 86. I didn't mention, but I should mention, one of the most common mistakes I see with this function notation, and it completely makes sense, I get why it happens, is that when we see that A of 94 is equal to 86, quite often our brain goes into overdrive and we think, okay, I can't stop there. I have to get A by itself because I'm looking for my average. That's just a name of the function. So your answer is 86. Your average on all 4 of these tests is 86 or 86%. So don't overthink it. If you see A of 94 and you have your function, that's really just telling you what to do. Your answer is just that 86. So here's a function right here. Q of p is equal to 4p minus 5. This question doesn't really have a long-winded word application and tests flying around or anything like that, but that's perfectly fine. If you're asked to find Q of 7 and you're dealing with functions, you should think, okay, well, I have to locate which function is Q. I only have one, so that's easy in this case. And then I'm going to plug in 7 for my input. So I'm going to replace my P with 7. I'm going to multiply that out. I'm going to subtract, and I'm left with Q of 7 is equal to 23. And again, it bears repeating. I don't divide both sides by 7. That's my answer. Q of 0, well, I take 0, plug it in for P, solve. 4 times 0 is 0, subtract 5, I get negative 5. Now be careful with this one. So this question isn't asking you to find a value of a function. It's instead asking you for you to find your input given that your output is 11. So I know that the result of my function will be 11. I don't know what my input will be. So what I do in this case is I replace my Q of p with 11 and I go about solving for p. Well, that's just fairly basic algebra. I add 5 to both sides, divide both sides by 4. I get p is equal to 4. More definitions. One-to-one. So one-to-one will feel kind of similar to what we were talking about with the definition of function. It's a function, but instead of talking about one input has to be mapped to a single output, now one output can only be mapped to a single input. So a lot of those examples that we saw at the beginning, if you want to go back and look at it, a lot of those examples were not one-to-one because we had those two outputs being mapped to, or we had an output being mapped to two separate inputs. So for this first equation, actually that might be from the first slide. I think it is. Well, we already saw it. It's a function. I have my inputs. I have 3 different inputs, so they can't be mapped. I can't have a single input going to 2 outputs. So boom, it is a function. Well, now we have to think, okay, is my function one-to-one? Well, we look at the outputs in this case. My outputs are -2, 5, and 5. So now I have repeating outputs. And my repeating outputs are mapped from 2 separate inputs for a -3, so this is not one-to-one. It is a function, but it's not one-to-one. Where in this case, okay, I have -2 being mapped to 1, I have 1 being mapped to 5, and so every one of my outputs only has a single input, so we're good to go. That is one-to-one. I don't know why I'm missing my hyphens there. Now there's a couple of ways to determine if a relation is a function and if it's one-to-one when looking at a graph. So if you have a graph, these are actually really nice and quick tests. And honestly, sometimes if you have a function and you're pretty good at graphing, it's not a bad idea to graph it and then use these tests to determine if it is a function or not, or if it's one-to-one or not. And so these 2 tests are named the vertical line test and the horizontal line test, which makes sense because one-to-one and the definition for one-to-one and the definition for function are so close to each other that the tests should be so close to each other. And how the tests work is, for vertical line test, we'll focus on that one first, is that if you can draw any vertical line that would intersect your graph in more than one spot, the graph is not a function. So these tests, you're trying to prove something is not a function. And very similar, horizontal line test, if you can draw any horizontal line in your graph and it intersects your function in more than one spot, then it is not one-to-one. So to see it in practice, this leftmost graph, I'm going to try and use the vertical line test on it. Okay, well, I drew a vertical line there. It's only hitting 1 point. One there is only hitting 1 point. One there is only hitting 1 point. I can play this game all day, but eventually you can kind of arrive at the point of saying, okay, it doesn't really matter where I put that vertical line. It's only going to hit 1 point on my graph. So it's definitely a function. Now I'm going to determine if it's a one-to-one function. So I go through the horizontal line test, and at this point almost like ignore those red lines. Now I'm moving on. I'm only concerned about that blue diagonal line. So I draw a horizontal line, only intersects that f of x function once. Another one, and again, I can do this all day. I will never intersect more than one or my graph at more than 1 point, so it is 1-to-1. I don't know if we can see the bottom of that, but I'll show the whole slide after. But all it's saying there is that it's 1-to-1. Okay, second graph. Same type of thing. I draw a vertical line intersecting 1 point, draw another vertical line, intersects 1 point. You can play this game all day. There is no way that you can draw a vertical line that will intersect more than 1 point. So it is a function. But now let's go to the horizontal line game. So this first guy, yes, I can draw one line that would intersect 1 point on my graph. But look carefully at that definition and specifically what is underlined in that definition. This has to be true for any line you could draw. So even though I drew one line there, that's the only line I can draw that will only intersect 1 point. So as soon as I draw a different line, like right there, for example, that intersects my graph at 2 separate points. So that is not 1-to-1. Last graph, same type of logic. Vertical line test, I'm trying to determine if it's a function or not. I can draw one line that would intersect 1 point. I could honestly draw another line on the other side of the circle that would intersect 1 point. But it would be very, very easy. I could give this graph to someone in 3rd grade and say, can you draw a line vertical that intersects 2 points? And they would almost do it immediately because there's so many options you can do it. So as soon as you can draw one line that intersects more than 1 point, not a function. And if you wanted to, you could go ahead and do the horizontal line test. But the truth of the matter is, if it's not a function, you can't really have it be 1-to-1. You need something to be in function in order for you to even kind of start the conversation about whether or not it's 1-to-1. So, I mean, you might be taking a not well-written test at some point in your future, and so they might ask you to determine if it's a function or not and whether or not it's 1-to-1. But if it's not a function, it can't be 1-to-1. Let me pull up that slide in case we can't see it. So this is what that slide, that's what we were missing, was the bottom part. So that first graph was 1-to-1, and the second graph was not 1-to-1 because we could draw that line that intersected 2 points, as we saw. Okay, let's get back to it. Now, moving on to, maybe we don't have a table, maybe we don't have graphs, maybe we just have a straight up equation like this. So I have my equation, x cubed plus y squared is equal to 5, and I want to determine if the following function is 1-to-1. So what I'm going to do is I'm going to get y by itself, and then I'm going to square root both sides. Well, that causes an issue because what that's describing right there is, let's just throw in a number for an example. Let's say x is equal to 0. Well, that means y could be my output. My output could be positive 5. And it could be negative square root of 5, positive square root of 5. Or it could be negative square root of 5. So that means that that input is being mapped to 2 outputs, and so it is not 1-to-1. And this is kind of a bit of a shortcut for what you'll see in the course, and it's not the best strategy when you branch out beyond this. But really, if you are taking a square root or maybe like a 4th root, anytime you're doing that plus or minus, that's going to kind of break your definition of 1-to-1, where if that's not happening, you probably have a function that is 1-to-1. Okay, the difference quotient. Now this is probably the most famous equation in calculus. So if you plan on taking calculus at some point in the future, make sure you feel pretty comfortable with this concept because you'll have to do it definitely a few times, at least as far as an introduction to what a derivative is. And so if we're asked to find the difference quotient, we have to find it for a specific function. So you have to be given a function. So here we're given f of x is equal to 4x minus 5. And now I'm looking at my difference quotient. I need a couple things. I need my f of x. Well, I already have that. That's great. I need my f of x plus h. I'm going to have to find that. And then h is just a variable, so I don't really have to find h. So in order to build that difference quotient, now I'm going to find f of x plus h. While I do that, With function notation, f of x plus h means that I'm going to take my function f of x, and I'm going to plug in x plus h into the x. I'm going to plug it into the input. So when finding f of x plus h, notice how it's almost the exact same equation, except for instead of having a single x like I have for f of x, now I have f x plus h replacing that x entirely. And then once you've done that, then you have to do a little bit of simplification. And yeah, the simplification get a little bit more complicated than this problem, but as far as the process goes, that's the idea. You take your function, you replace your x with x plus h, ideally in parentheses, and then you simplify. So that's my f of x plus h for this. My f of x is already given to me, so I don't really have to find that at all. And now I just put those into my difference quotient. So f of x plus h is now replaced with what I found, 4x plus 4h minus 5. And f of x is replaced with what I was already given, 4x minus 5. Now it's a very good idea to put that function in parentheses because we're subtracting every time we do the difference quotient. And so we're going to want to make sure that we distribute that negative sign to both things inside my function. So I'm going to do that. So all that does is becomes a minus 4x and then a plus 5. And now I simplify as far as possible. So my 4x's will cancel out, my 5's will cancel out. And now here's a very important step, or at least an important checkpoint along the way. So one of the cool things about the difference quotient is that if you are doing all of your steps correctly, your h's will always, always, always cancel out. So if you get to this step in the process and you have a 4h plus a 6 flying around at the end and you can't really cancel out all your h's, you did something wrong. There's a good chance you flipped a negative sign. That's usually the issue, but that's super nice to be able to say, oh, actually, that's not how this equation should break down. Let me go back and see where I made my mistake. And so my 4h over h becomes 4 because my h's will cancel out, and that is the difference quotient. That is the end of this lecture.